and then share my screen. All right, so we're recording now, and I'll post this on YouTube afterwards, and I'll send you the link. And here are the solutions. So problem set number one, the first one says the motor, and this is actually, I think this is actually my motor in my electric motorcycle. That's originally why I wrote it this way. It's 23 kilowatts. How many horsepower is this? So that's just a unit conversion problem. And in a unit conversion problem, basically you're just multiplying by 1, where the numerator is equal to the denominator, but just in different units. And that's how we do our unit conversion. We want to cancel out the units that we don't want in the answer, and we want to get to the units that we do want in our answer. So we start with kilowatts here, 23 of them, and we want to get to horsepower. And we're given the unit conversion, 1 horsepower equals 746 watts. So I wrote that down first. But that doesn't really get us able to cancel out kilowatts. So in order to do that, I have to put another conversion factor here where 1,000 watts is equal to 1 kilowatt. Then I can cancel out my kilowatts there, and I cancel out my watts there, and the only unit left is horsepower right here. So I know I'm going to get the right answer because my units work out. So now it's just a matter of plugging it into the calculator. 23 times 1,000 divided by 746 gives you 30.8 horsepower. And by the way, if you have any questions about anything on here, I'd honestly just prefer if you just kind of interrupt and butt in, because it's easier that way than putting something in the chat, I think. So if you put something in the chat, I'll try to look at it, but it's probably easiest if you just ask your question, because I can't even see all of your faces right now. So if you're raising your hand, I can't even see all of you right now. So just interrupt if you have a question. Number 2, I think this is actually real data also from my refrigerator. I'm kind of embarrassed that I'm kind of embarrassed by the number of refrigerators I have in my house. So we have one in the kitchen, and then we had to, well, the next one we got actually was my beer. It's a mini fridge, but it's a mini beer fridge in the basement. It's just big enough to hold 2 5-gallon kegs. So I'm not talking like the giant barrel kegs. I don't brew in that size of batches, but they're 5-gallon kegs. They're maybe 8 inches in diameter by 30 inches tall, something like that. So it's enough to hold 2 of those and a bottle of compressed CO2. So I've got that mini fridge down in the basement, and then we've also got kind of like an apartment-sized fridge down in the basement. With a family of 6, we just found that it was really hard to keep enough frozen pizza, for example, in the freezer in the kitchen. It just wasn't possible. So anyway, I am kind of embarrassed about the number of refrigerators, but as soon as we got that 3rd refrigerator, the apartment-sized one in the basement, I started monitoring them with a kilowatt meter. So I've got most of my refrigerators hooked up to a kilowatt meter so I can monitor how much power and energy they're using. So this is one of my refrigerators. I think this might have actually been the kitchen refrigerator in my house. I'm not positive though. Anyway, it draws about 0.6 amps when it's running. It runs about 76% of the time. How much energy will it use per year? So like we talked about at the very end of class last time, there's an assumption you have to make here because it doesn't tell you the voltage. And you're going to need to know that in order to calculate the power, which you need in order to calculate the energy. So you have to make an assumption. And since we're in the United States and the standard wall outlet voltage anywhere in North America actually is 120 volts, you can assume that the voltage applied to this refrigerator is 120 volts. So we can use that to calculate the power that it's going to consume when it's running. So the power is current times voltage. That's 0.6 amps times 120 volts. And that gives us 72 watts of power when it's running. And the next step, you can do this in a couple of different ways. You don't have to do this in the exact same order that I did it. But the way I did it here is I calculated the amount of energy it would use for the whole year if it was running for the whole year. And then I know it's actually only running 76% of the time. So I took that answer times 0.76. That's the way I did it. But there are a couple of different ways. And it doesn't really matter what order you do this since you're just multiplying stuff together anyway. So what I did is I used the equation energy equals power times time. The power is straight from the previous part, so that's 72 watts. The time, I know I want to get into kilowatt hours, so I want to get the time in hours, and I also want to convert watts to kilowatts. That way, when I multiply, I'm going to get kilowatt hours, and I want to get that per year. So to get the delta T, I take 24 hours per day times 365 days per year. And then to convert into kilowatts, I take that times kilowatts per 1,000 watts. And then stop and look at this for a little bit and see what your units are doing. So I'm going to be able to cancel out watts here and days here and here. And what am I going to get left? I'm going to get kilowatt hours per year, which is what I want in this step. So that's exactly what I want to do in this step of the calculation. So I multiply all those together and I get 630.7 kilowatt hours per year, but that's if it was running nonstop throughout the year. It's not, it's only running 76% of the time. So I take that number from there times 0.76 and I get 479.3 kilowatt hours per year, which is not bad. You can do a very rough calculation. You figure a kilowatt hour costs about 10 cents, usually a little bit more, but call it 10 cents. So this costs me to run that refrigerator, it costs me about $50. If it's 10 cents, then it's $47.93, but it's probably a little bit more than that per kilowatt hour. So about $50. That's about what I pay per year to run this refrigerator. But the question is just how much energy per year. So there it is. And then number 3, we talked a little bit about this last time because I knew it was on this first homework set. So I spent a little bit of time talking about this. What does a kilowatt per hour mean? Like I said, it's not meaningless, but it usually doesn't mean what people think it means. It's a unit of power per unit time. So what does that mean? Usually the application of that would be something called a ramp rate, which is how fast can a generator come up to power, how fast can it increase its power, or how fast can it decrease its power over time. And these types of thermal power plants, like a natural gas combined cycle plant or a nuclear plant or even a biomass, like a solar thermal plant or a biomass thermal power plant, these thermal power plants, it's not like you can just switch them on, like boom, they're at full power. It doesn't work that way. You got a lot of steel inside the boiler and the condenser and the turbine and the pipes. There's a lot of components in there that have to be warmed up. You can't just flip a switch and have them operating at full power. It doesn't work that way. So as an example here, one example, when I used to work on a nuclear power plant on an aircraft carrier, we would start warming up the system and eventually starting up the system, coming up to power 24 hours, a full 24 hours before we intended to actually get underway. When the ship was leaving, everyone in propulsion department was there on the ship a day before, a day ahead of time. So that was kind of a bad thing about being in the propulsion department. You're usually like the first ones on the ship before you get underway, and you're oftentimes the last ones to get off the ship after you pull into port. A civilian nuclear power plant, it has a ramp rate as well, or a warm-up period. Pretty common numbers for a civilian nuclear power plant are about 100 megawatts of electricity, 100 megawatts electric per hour. So if it's a 1 gigawatt nuclear power plant, which is pretty standard, it would take about approximately 10 hours. But it's a little bit more complicated than that, because once you get up to about 90% power, then there's a lower limit, a lower ramp rate allowed between that 90% and 100% level. Usually something like 10 megawatts of electric once you're above 90% power. So that's enough for me to say about that. I want to emphasize that you don't just turn on a thermal power plant like that and expect to be at full power. There's a ramp rate. You have to increase the power slowly. And then the last one, number 4. All right, this is me like a week ago pulling my kids in a sled. and they're very happy, and I don't appear to be quite as happy pulling them across the ground. And it says that we have a force in this direction of 200 newtons, and the angle theta between the direction of motion, or the ground, and the force is 60 degrees. So this angle theta is 60 degrees. And I'm pulling it across a 100-meter wide field, and we want to know how much work did we do. All right, so we've got a force that is applied, but it's not applied at the same angle as the motion's going to be, so we have to use that theta. And we have a distance that's 100 meters. So this is kind of just plug and chug here. Work equals force times distance times cosine theta. And we're given what the force is, we're given what the distance is, and we're actually given theta as well. So you just plug in cosine of 60 degrees times 200 newtons times 100 meters, and you get 10,000 Newton meters. But it's helpful to know that 1 Newton meter, if you exert a force of 1 Newton over 1 meter of distance, that's a joule. So 10,000 Newton meters is equal to 10,000 joules. So that's the best answer, is 10,000 joules, or 10 kilojoules. That's fine also. And the very last part is about power. It took me 45 seconds to pull this sled. How much power was I providing to the system? So power is a rate. It's a rate of energy being transformed or of work being done, either one. And so in this case, we have this amount of work being done per unit time. So I can plug in numbers for the work and the amount of time that has elapsed. So I've got 10,000 joules and I've got 45 seconds. So you can divide those numbers and you get 222 joules per second. And now you can recognize that, oh, a joule per second, a better name for that is a watt. So I've got 222.2 watts, but it asks for it in horsepower. So you just got to convert that like we did in problem number 1. So take 222.2 watts. You got to get rid of the watts. So put that in the denominator and put an equivalent term in the numerator. 1 horsepower is equal to 746 watts. So watts cancel out, and I get 0.3 horsepower. That's about right. Those numbers are pretty realistic. A human can sustain about 1/3 of a horsepower for quite a while. That's like a good aerobic exercise. You can probably sustain maybe 1/2 or even maybe 2/3 of a horsepower, but only for a very short time period. All right. So I will stop recording